Hello, hello. Okay, very good. All right, so welcome to the session on lattices in the LPN. We have 4 talks in the session, and the first talk is on vanishing short integer solutions revisited, and Russell is giving the talk.
Testing. Yeah, thanks, Alex, for the introduction. So I'm Russell, and today I want to talk about the vanishing short integer solution, or VCs, which is an assumption that I introduced 2 years ago. And this is a joint work with my former master student, Kalle Jyrkinen, who unfortunately cannot make it here. Okay, so VCs is a variant of CIS, and so let's start with recalling what CIS is. So I'm sure you're all familiar with CIS nowadays. So a CIS instance is given by a random matrix A, wide, and the task is to find an integer vector x so that ax equals 0 mod q, and x is short, so like its norm is small. So it is well known that CIS, which is an average case problem, is as hard as the worst case problem of shortest independent vector problem, or SIVP, which is believed to be hard even for quantum computers, and that's why we have post-quantum security. And on top of that, we know how to construct trapdoors for CIS. So we know how to sample a random CIS instance A together with a trapdoor, so that given any image y, we can sample a short vector x so that ax equals y. And because of this versatility, there are many applications of CIS, including, for example, homomorphic signatures, which I'm going to talk about later in this talk. And so originally, CIS was defined over integers, but then soon later, people discovered that you can generalize it to rings and modules, basically add more structure to get concrete efficiency improvement. And the same story can be, more or less the same story can be said for LWE as well. And all this is basically well established, say, more than 10 years ago. But recently, there is a trend of considering hinted and or structured lattice problems. So here by structured, I mean going beyond ring and module structure, but to, for example, consider polynomial structure. So even more structure to the CIS and also LWE instances. And so the reason why we care about this structured and hinted assumption is usually for 2 reasons. So first is that we may get practical advanced primitives like snags, or they allow us to achieve new functionalities which was not possible before. So in this talk is loosely related to this family of structured and hinted CIS assumption family. And the first member here is called basis augmented CIS, or basis, introduced by David here and Hotek. And it was used to build the functional commitment for circuits. And then, so basis is, let's say, not weaker as an assumption than something called K-ring inhomogeneous CIS, or crisis, that we introduced back in 22. And it was also used to build functional commitments, first for low-degree polynomials, and then for circuits. And a closely related assumption is strong hinted VCs, which Adrian talked about yesterday, and we used it to build proof-friendly signature schemes. And then finally, arguably the weakest assumption of all in this family is actually vanishing CIS, or VCs. And it is used to build the currently most practical lattice-based snags. So as you can see, VCs is the weakest assumption among here, and meaning that it's the hardest problem among here. So if we manage to break the VCs assumption, then we can also break all the other assumptions in this family. So it's quite important to understand fundamentally how hard is VCs. And that's exactly what we do in this work. So I've been talking about VCs, but what is it? So let's focus on a simple variant, which we shall call simple VCs. So this problem is parameterized by a polynomial degree d, which we assume to be constant for now. And the problem instance is given by a random point v, sample from some domain, modulo q. And the task is to find a degree d polynomial, p with short coefficients, so that p of v is 0, modulo q. Or in other words, p vanishes at v, modulo q, and hence the name vanishing cis. So with respect to this problem, we present the following 3 results. The first result is a reduction. So we show that the worst case of simple VCs is as hard as finding short vectors in some ideal lattices, in a certain class of ideal lattices. And then secondly, we can construct VCs trapdoors, assuming that the decision and true assumption holds. So these trapdoors allows us to sample a random point together with a trapdoor, so that when we are given any target value, we can sample a short polynomial that evaluate to this target value at the point v. And so to showcase these trapdoors, we decided to build a homomorphic signature scheme, which has the cool property of being fully algebraic. So namely, it does not use any B-ary decomposition operation. So it's purely ring operation. Okay, so that's an overview of our results. And next, let's get to the technical details. So we will be focusing on the F cyclotomic field, and F stands for the conductor, if you know what it means. So R is the ring of integers of K, and the degree of the field is phi, which is also the Euler-Toscan function of F. And as a trivial example, the first cyclotomic field is just the rational numbers, and its ring of integers is just a set of integers. Another popular example are power of 2 cyclotomics, which are isomorphic to these polynomial quotient rings. And the degree would be 2 to the k. Okay, so to understand the connection between cis and vcis, it's quite helpful to take an alternative function point of view. So again, in a traditional point of view, a cis instance is given by a wide random matrix A, and the task is to find a short vector x so that ax equals 0 mod q. From an equivalent function point of view, we can view each row of the matrix A, each of the n rows, as a random point in some m-dimensional space. And with this view, the problem now becomes to find a linear function f with short coefficients that vanishes at all the n given points. So with this point of view, it is easy to see that you can generalize it, the problem, by allowing f to be other functions, for example, polynomials. And that's precisely what we consider in this work. So in particular, we consider the simple case where there is only one point. So, so n is equal to 1. Formally, we define this VCs R, D, Q, beta problem, where a problem instance is given by a random point V in the cyclotomic ring, modulo Q. And the task is to find a degree D polynomial, D is specified here, with coefficients over the ring, and such that P of V is 0 modulo Q, and the coefficients of P are bounded by beta. So for concreteness, we can think of the ring degree as being linear in the security parameter, so something like 500 to 1000. And the polynomial degree D is constant, so say 1 to 10. And the modulus Q is polynomial, and the norm-bound beta is also polynomial. When D equals 1, then we essentially recover the search and true problem, except that in n-true, traditionally, we additionally require that the problem instance V is of the form F over G, where F and G are low norm random elements of the ring. Okay, so with these preliminaries out of the way, let me present our technical results. So the first result is a reduction from ideal Hermit shortest vector problem, or gamma ideal HSVP, to simple VCs. So this problem, gamma ideal HSVP, is defined as follows. So a problem instance is an ideal of the ring. The ideal is denoted by I. And the task is to find an element x in the ideal so that it is at most gamma times longer than the shortest element in the ideal. Or in other words, its norm is bounded by this expression. Okay, so against this problem, we have the following to say. So let d, the polynomial degree, be constant, and let the ring degree be polynomial, or more specifically linear, in the security parameter, and let there further be two extra parameters, theta and n, which are also polynomial, and let the norm-bound beta, the modulus, and the approximation factor be defined as such. And the important thing is that because d is constant, so these are all polynomials in the security parameter. Okay, so with respect to these parameters, we say that the worst case of VCs with modulus q to the d and norm-bound beta is as hard as the gamma ideal HSVP problem for ideals with the following restrictions. So first, we require that the algebraic norm of the ideal is at most n to the phi, where n is defined here. And also, the ideal should be of the form, should be represented by some field element z, and it is equal to the intersection between the principal ideal generated by z to the d intersecting with the ring. And furthermore, we want that the inverse of z has upper bounded norm. Okay, so yes, that's the theorem. And to prove this, the basic idea is to generalize an existing reduction given by Pellet-Marie and Steller, who gave a very similar reduction from ideal HSVP to n true, and which is basically degree 1 VCs, and we generalize it to degree d. So the reduction itself is actually very simple, but the analysis is quite complicated. So the reduction takes as input I, represented by z. It computes q over z and round it to the nearest ring element in the coefficient embedding, take modulo q to the d, and feed this to the adversary, who outputs some polynomial. And supposedly this polynomial vanishes at v, modulo q to the d, and it has bounded coefficients. And so regardless, the reduction simply outputs the leading coefficient of p. So if I have to summarize the reduction in two sentences, so let me say this. So as a thought experiment, we think about the shortest element, alpha, in the ideal. And then we examine this relation here. So we examine alpha, the shortest element in the ideal, times the leading coefficient of the polynomial divided by z to the d. And then we somehow show that it is equal to alpha times some ring element r. And then once we do that, we can cancel out alpha on both sides, and then we conclude that indeed the leading coefficients belongs to the ideal generated by c to the d. Okay, so there are lots and lots of limitations of this reduction. So first of all, we focus on the univariate case and with constant degree, and the polynomial vanishes at a single point. So beyond that, we have quite a bit of restrictions over the ideal I that we can have a reduction. And also, the V6 instance that we reduce to is with modulus q to the d rather than q. So in particular, we don't cover the case of prime moduli V6. And finally, our reduction is worst case to worst case and average case to average case. So ideally, we want a worst case to average case reduction. Okay, so as a second result, we present trapdoors for VCs. So recall that the trapdoor for cis allows you to sample a random matrix A together with a trapdoor, so that given any target y, you can sample a short vector x satisfying ax equals y. And similarly, a V6 trapdoor is such that you can sample a random point V together with a trapdoor, so that for any target R, you can sample a short degree D polynomial that evaluates to R at the point V. So the idea here is basically, again, to generalize existing n-true trapdoors, which are essentially degree 1 VC's trapdoor, to the degree D case. And the trapdoors that we managed to sample are of near optimal norm. Namely, their norm is roughly the D+1 root of Q. And so note that even the n-true trapdoor algorithm is only heuristically polynomial time, and so does our algorithm. Okay, so here are some small-scale experimental results of our trapdoors. So to summarize very briefly, these are the plots for degree 1, 2, 3, 4. And the intersection between the two solid lines is the lower bound, theoretical lower bound of the norm of the trapdoor. And these dots are the trapdoors that we managed to sample. And as you can see, these there exist some points, some dots, which are close to this optimal value. And therefore our trapdoor is close to optimal. Okay, and again, usual limitations. We only support a constant degree univariate polynomial vanishing at a single point. So here I should mention that even for the n-true case, doing it for multiple points is already an open problem. Okay, so finally, let me demonstrate how to build homomorphic signatures from VC's trapdoors. So for those who are not familiar with homomorphic signatures, the idea is simply that you can sign some vector x so that someone can publicly evaluate the function g on the signatures to produce a signature of g of x. So suppose we want to sign an n-dimensional vector x. Then during setup, we sample n random ring elements, R1 to Rn. And the public key would be a VC's instance, and the secret key would be a VC's trapdoor. To sign the ith message, xi, we sample a short degree D polynomial, fi, so that fi of 0 is xi, and fi of vi is ri. And this can be done using the VC's trapdoor. So given this, the homomorphic evaluation is very simple. So suppose we want to homomorphically evaluate a low norm polynomial g, multivariate polynomial g, then we simply evaluate it at the signature polynomials, f1 to fn. This will give us a new polynomial h, which will be the signature. And finally, to verify this signature for the tuple gy, where y is supposedly g of x1 to xn, then we simply check that h of 0 is y, and h of v is g of r1 to rn. Okay, so formally we say that assuming decision n true and VCs for appropriate parameters, then we get homomorphic signatures for low norm constant degree multivariate polynomials. So this construction is more of a demonstration and it's not really practical, and there are two efficiency bottlenecks. So first is that the description size of the signature grows at least linearly in the multiplicative depth of G, because the degree grows. And secondly, more importantly, its norm grows exponentially in the degree of G. Okay, so to summarize in this work, we present three results about VCs. The first is a reduction from ideal HSVP to the worst case of simple VCs. And we construct trapdoors for simple VCs and use it to construct homomorphic signatures. So there are many open problems behind each of these results, but in my opinion, the most important is to obtain a reduction from some worst case problem to VCs for beyond constant degree polynomial, because that's what the current lattice-based NARCs are based on. And in case you don't care about VCs, then I still encourage you to look at other structure and hinted assumptions. Thanks.
Questions for Russell?
Thanks for the talk. as you said, you had quite a few restrictions on the ideals in your reduction. Have you tried plugging in any concrete things that we assume to be hard that satisfy these?
No, it's really difficult to navigate between all these constraints.
I see.
We are not even sure if such instance exists.
Okay. Okay. Thanks.
More questions? I have one. For this, you were really talking about max norm, right? Because you said you want to bound the coefficients. Does it imply anything for other norms like L2?
So typically people talk about L2 norms.
Yeah, for Falcon, it's more L2, right?
Right. I think there are reductions between different norms, but yeah.
Yeah, so in principle, it holds for any norm.
Yeah, I think like pick any norm you like.
Yeah,
It
I see.
will be
I
interesting.
see.
Yeah.
Okay, nice. Okay, if there are no more questions, then let's thank Russell again. This is a PowerPoint?
Yes, PowerPoint.
Yeah, okay. I think this is this one. And now we have to switch to... Yes, here we go. You good? Perfect. Okay, perfect. Let's go to the second talk. This is on discrete Gaussians modulo sublattices. New leftover hash lemmas for discrete Gaussians, and Hua Zhang is giving the talk.
Thanks for the introduction. And I'm Hao Xiangjin, the speaker. This is a joint work with Feng Hao, Zhe Dong, and Da Wu. So let's begin. As a cryptographer, all the belief we hold is that the randomness is very useful. Think of the very simple scheme one-time pad. We need the full randomness compared to the message to fully cover the message. So randomness is so powerful. So how to obtain it? Well, the tool is randomness extraction. So we crucially need some randomness, ideal randomness in many areas in cryptography. However, we often deal with some imperfect sources. For example, the sources are taken from some physics sources, biometric data, and also we have some leakage about some secrets. So can we extract some randomness from U-behaved random variables? The key notion in this field is leftover hash lemma. Well, because in the lattice world, we often deal with randomness extractor, which is inner product over finite field. So think about the finite field ZQ. The public matrix is uniformly taken from ZQ to the n times m, and X follows some potential distribution which has high mean entropy. So that from the leftover hash lemma, we can state that the joint distribution of A and A times X is uniformly at random. This is a very simple and useful randomness extractor. Well, in the ring case, things seems to become very complicated because the ring modulo some Q, RQ, where the ring R is some cyclotomic field. RQ is not any finite field. So in this case, we also can apply the leftover hash lemma. Our guarantee is that for any ideal factor I of the QR, and X modulo I should have high entropy. This is a result obtained from ILL 89 and Micciangelo 11, the very seminal papers. And here are some brief introduction about lattices. Of course, the lattice is composed from a basis. A basis is composed of n linearly independent vectors, and we take all the integer combinations of them to form a lattice. It is very useful in the post-quantum cryptography and also in FHE. And our focus of this paper is to compute the certain mean entropy of some discrete Gaussian distributions, of course modulus some sublattice. So what is a discrete Gaussian distribution over a lattice? We are familiar with what is a normal distribution, a continuous version. And for the discrete version, we need the support restricted to the lattices. So we have the same mass function, which is rho sigma of x. And when we define a discrete Gaussian over a lattice, we need to compute the ratio of rho sigma of x over rho sigma of the whole lattice. So this is our focus. So what if the source of we need is a discrete Gaussian over the lattice? Our target is that show that the public matrix is A, and then S is chosen from some discrete Gaussians. We need to compute that the statistical distance between the joint distribution of A and A times S with A and some uniform vector U. So there are some existing results, also called the regularity lemma, in the very seminal paper by Gentry, Packard, and Vakutanathan, 2008. They use some strategy called the smoothing parameter. So their restriction is that the sigma, which is Gaussian parameters, should be inherently larger than some smoothing parameter of the Q-array dual lattice of the public matrix A. So if you are familiar with smoothing parameters, this can be computed with approximation to omega of square root of log of n. And in a ring case, things also becomes more complicated. And in 2013, Lubashevsky, Packard, and Regev also gave a similar result over the ring. Well, they take the ring R to be some cyclotomic field, and their public matrix are chosen in a form. The first is one identity matrix, and the second one is the uniform matrix. So the public matrix is the concatenation of two matrices, and then they compute that the sigma should be larger or equal to the smoothing parameter of the same dual lattice, which is approximately all of n. I have to state in this way that the sigma are considered over canonical embedding to assign to the ring. So one question is that is it inherent to require the sigma which is larger than the smoothing parameter? Because we have some tools to sample some sigma that are smaller than the smoothing parameter if we set the lattice to be the integer. Well, another question that if we further consider some source leakage, for example, the other parts of the level hash lemma are the same, but well, the difference is that we have some auxiliary S, which is considered as the leakage. Well, the technique based on the smoothing parameter cannot handle this case. So this is the second question, how to show a level hash lemma for discrete Gaussian to handle the source leakage. The idea is quite simple. We can just compute the certain mean entropy and then apply the existing level hash lemma to it. So here is our way of computing the mean entropy. The first question is why we consider the discrete Gaussian modulo sublattice. You can see that lambda is the original lattice, and lambda prime is one of its sublattice. We hope that it is the full rank sublattice of lambda. Because you can see that in the two cases, one simple case is the integer. The lambda is chosen to be Zn, and lambda prime is chosen to be Qzn. And in the ring case, lambda is chosen to be the ring of integers, and lambda prime is any ideal factor of QR. So an ideal, the lattice related to an ideal is very easily to proven to be the sublattice of R. So how to compute the mean entropy? One key relation is how to compute the shifted sum of some lattice in a both way. Well, one way is to make it less than the sum of Gaussian functions with no shift. Well, the other way is that we just times another factor that's smaller than 1, which is rho sigma of C. C is a shift. So we can first to compute the mean entropy of this sort of distribution, which is larger than the log of some logos of the sum of the Gaussian functions, where the subset is chosen from any set of the coset representatives of lambda modulo lambda prime. Lambda modulo lambda prime can be regarded as a quotient group. So let me give you an example. For the very simple integer case, this 12 example, you can see that the lambda modulo lambda prime is very easily to be considered as CQN. Of course, we would like to make this quality of the coset representatives as good as possible. So we need to choose the vector inside as small as possible to make the sum as large as possible. So for the integer case, we can easily chosen that CQ to be minus half Q to half Q intersected with the integer. And this sum is very similar to rho sigma of Zn. This is a result by BN95. And this result similarly illustrates that the Gaussian sum of a lattice concentrates on the sphere or on the ball. So it has no contribution outside the ball, because you can easily imagine that the Gaussian sum outside the ball degraded very exponentially. And for Miccianto and Regev 2004, this term is very similar to sigma to the n. So the final result is n times log of sigma. This is just a toy example. And for the ring case, the strategy is still to show what is the good coset representatives of the lattice over sublattice. Here we use the Dedekind theorem. The Dedekind theorem illustrates that for any Q prime and for a factor which is an ideal divisor of Q times R, and I can be written as two generators. One generator is exactly Q. Another generator is some polynomial f of x. Well, I is not necessary to be the prime ideal of QR. This is some discovery which generalizes that kind of theorem. So if the norm of the ideal is equal to Q to the T, and then the degree of f is equal to T. So we can imagine that what is R modulo I. R can be considered as the integer polynomials, and first we need to modulo Q. So all the coefficients becomes ZQ, and second we modulo f of x. Then the degree of the polynomial becomes less than t. So we can choose ZQX where the degree is less than Q to be the quotient group. And here we concentrate on the coefficient lattice. Phi is the coefficient embedding. Here we can easily compute that the mean entropy of the discrete Gaussian over the ring of integers modulo I is larger than or equal to t times log of sigma. Another observation is that this t related to this t. These two things forms a somewhat linear relation. So our next step, we do not make any new contributions to the fundamental level hash lemma. We just put our result of mean entropy to the level hash lemma, then compared the result with the previous regularity lemma. So you can see in the integral part, here is our restriction or constraint on the parameters. Well, the GPV8 requires that sigma is inherently larger than the smoothing parameter. Well, the smoothing parameter counts something. So we give a new trade-off between n and sigma, and also sigma can be saved by a factor of omega of square root of log of lambda. Well, for the ring case, you can see that we restrict Q to be prime. And if Q is in this number theory form, and QR can be decomposed into this way. And if we choose F to be 1, this scenario is called fully splitting. This lemma is obtained from Lobachevsky and Saylor 2018. And we can see that each norm of Qi is exactly equal to Q to the F. And Qi is any prime ideal of QR. And this is our result for the trade-off of M, F, N, and sigma. It also holds for when the ring QR is fully splitting. In LPR 13, they require that sigma is implicitly larger than 2 times square root of n. So sigma actually saves a factor of square root of n. And our result or our trade-off is also holds for concrete cryptographic design, because this sort of hash lemma is widely used in recent submissions to or accepted papers to crypto and Eurocrypt. I remember that some commitment scheme and some signature scheme Raccoon use this. So one application of our lemma is a harness of extended modulo LW. And this sort of extended modulo LW actually is one of the assumptions in the family where Russell talks about. We have some leakage. The leakage is some public vector Z and the inner product between Z and phi of S. Remember that phi is the coefficient embedding. So the reduction also actually follows the paradigm of Brakersky and Nico Dodling 2020. And first, we use the lossy argument to change A to BC plus F. And second, we decompose the E into FE1 plus E2. And in in Brokersky and Nikodoling's paper, they argue that S condition on S plus E has a high entropy if the S has high entropy initially. But here we can use a very different analogy to analyze it, because E1 follows some Gaussian distribution, and S also follows some Gaussian distribution. And S condition on S plus E1 follows another distribution with some sort of shift and a different Gaussian parameters. If sigma 1 is far more larger than sigma, then this actually does not affect the sigma too much. So in this case, we can compute that C concatenated with A times S is uniformly at random via our new left-over hash lemma. And some open question related to this work is that can we generalize the left-over hash lemma to more general lattices? Remember that we restrict our left-over hash lemma to the Gaussian distribution over the integral lattice and the ring of integers. But in some GSW ciphertext randomization, which is proposed by both Pino, Minli, and We 2016, they require a left-over hash lemma of discrete Gaussian distribution over the dual lattice, the Q-area dual lattice related to the gadget. So thanks for your attention.
Thank you very much. There's time for a quick question. So maybe I have one. If you compute the min entropies, you compute the min entropy of a discrete function, but then you take the PDF of the continuous function. That's what you do, right? And I wouldn't know how to do it discretely. I mean, you cut off the tails, that's what you said, right? But then
we do not cut off the tails. We just compute it directly.
Okay. But using the continuous function, that's what you do, no?
So
the e to the minus p.
I think the discrete Gaussian is defined, or it is defined by the continuous function, but in a discrete way.
Okay, but then you take the full infinite support. I mean, it has infinite support, right?
No.
Okay. You can compute it directly. I'm interested. Yes. Okay. Good, very good. So let's thank the speaker again. Okay, let's continue. Maybe?
Use this.
Yeah.
Okay.
Let's test.
Perfect. Good morning, everyone. I'm a PhD student from China, and it's my honor to be here to share our work with you. My topic is memory-efficient BKW algorithm for solving the LWE problem. My talk will be divided into 4 parts. First, I will introduce the background of LWE and BKW algorithm, and then I will introduce BKW technicals in a unified framework, and then I will give our main contributions, and finally, I will give a comparison and conclusion. With the development of post-quantum cryptography, the lattice-based cryptography has gained widespread attention. Among these, the learning with errors problem and its variants are one of the most promising problems in this field. Look at this LWE equation. The search LWE is to find secret S given many noisy equations, and the decision LWE is to distinguish the LWE distribution from uniform distribution. As many post-quantum cryptographic based security on LWE, so it is important to design efficient algorithm to attack it and accessing its harness. So it is very important for the cryptanalysis of LWE-based cryptography. Here are the exciting attacks on LWE. It can be divided into 4 categories. The first is combinatorial attack. It may include the BKW algorithm and meet-in-the-middle attack. And the second is exhaustive search. And the meet-in-the-middle attack often use it. And the third type is the lattice attack. And it can be further divided into dual prime multicoding. And when it combined with meet-in-the-middle or exhaustive search, it is called the hybrid attack. And the final type is algebraic attack. Mainly it involves the AJ algorithm. And in this paper, we mainly focus on the BKW algorithm. The BKW algorithm was originally proposed to solve the LPN problem, and then it was extended to solve the LWE problem in 2013. It is inspired by Wagner's generalized birthday attack, and this algorithm doesn't rely on any underlying lattice structures, and it doesn't rely on some lattice reduction algorithms. Let's outline the framework of the BKW algorithm. It has 2 phases, the reduction phase and the solving phase. In the reduction phase, the BKW algorithm iteratively reduces the LW matrix A, and each reduction step can reduce B positions to 0. And until the solving phase, we get a much smaller LW problem with small dimensions n prime, which is much smaller than n, makes this problem easier to solve. Let's take a closer look at how BKW works. In the reduction phase, if we have 2 vectors, their sum all differences can zero out B positions to 0. We can get a new sample vectors. And then the corresponding Z terms also changes, and the noise is bounds. In the solving phase, we need to distinguish the new reduced LWE. We can guess the secret S and to compute the noise distribution. If the noise distribution follows a discrete Gaussian distribution, we think we guessed correctly. And if it follows a uniform distribution, the guess is wrong. So in this, by repeating this way, we can recover the full secret vector. Now, here are our motivations and contributions. First, we found that the BKW algorithm requires a lot of samples in the reduction phase, which may lead high time and memory complexities and limits its practical attack. And there is little research on the memory constrained optimization on the BKW algorithm to solve the LWE problem, and there is no systematic time-memory trade-offs for the BKW algorithm to solve LWE. So we want to fill this gap. And then we did the following things. We gave a unified framework for all the reduction and solving technicals in the BKW algorithm, and gave a memory-efficient BKW algorithm, mainly divided into 2 parts. The first is some reduction technicals for low memory regimens, such as C-sum PCS BKW, and then we use graphs as a meta tool to give an improved memory optimizer FineOut automated. So let's look at the first part, BKW technicals in a unified framework. The first type is the LF1 or LF2 reduce. It can group column vectors of matrix A by absolute values at selected B positions. LF1 is to add or subtract a fixed representative from each group, and LF2 is a heuristic improvement of LF1. It can add or subtract any pairs within each group. And the second type is to combine lazy modular switching. It can reduce an LW instance mod Q to a scaled instance mod P, with P is less than Q. It may introduce running noise. We won't go into detail here. And the third type is combined with linear lattice codes. If the sample vectors mapped to the same code word, they can combine with each other to create new samples. This work will introduce coding noise, but if we can incorporate lattice shaving, we can control the progressively increasing coding noise. And all these reduction technicals are well documented in the following references. There are also other reduction techniques such as transform secret can convert secret distribution to a noise distribution, and the guess reduce can randomly guess B positions of the secret vector, and the discard reduce can discard samples with 9 zero values in the randomly selected B dimensions. For all the reduction techniques, we analyze how the sample size changes, how the noise changes, and we give the time complexity of them. And now there are the solving techniques, which is used to distinguish the discrete Gaussian distribution and the uniform distribution, such as the first optimal solver. It computes the log likelihood rate of two distributions based on the Nierman-Pearson lemma, and the FFT solver. We can first design a function and then compute its fast Fourier transform. And if the candidate can maximize the real part of F alpha, we can think it is a correct guess. And the Prand FFT solver is improvement of FFT solver. Here I will introduce our memory efficient BKW algorithm. I will start with several efficient reduction techniques for low memory regimes. It's all based on the multiple King-Linear finding, and we highlight the C-sum PCS BKW, which we will introduce in detail, and give some time memory trade-off comparisons of them. First, look at the C-sum technique. The key advantage of C-sum technique is that the C-element subsets will grow exponentially, which can reduce the number of entitled samples in the reduction phase. In turn, it can lower the memory use. So first, we define the C-sum problem. We can see if a single solution of this problem is a subset of C vectors that sum to 0, and a complete solution is to identify n distinct C-size subsets of B-dimensional vectors in L. And in the bottom, we give the complexity of C-sum BKW like this, and n has a lower bound. Now I will introduce how to combine with PCS, parallel conclusion search. To satisfy n lower bound, we set n like this, and then we split list L into C equals sublist Li, and we need to define two mapping functions, F0 and F1. Look at this formula. F0 can map the first C/2 subsets into a C/2 sum problem, and the F1 can map the remaining C/2 sublist to the C/2 sum problem. If a conclusion occurs between F0 and F1, we can obtain a single solution, and we can identify n distinct conclusions between F0 and F1 using the procedure PCS. And this figure is an example. The left is C equals 4, and the right is C equals 8. It is essentially split C-sum into two systematic C/2 sum and use PCS to detect sample conclusions. Now I give the complexities of the C-sum PCS reduce in the above formulas, and to get the corresponding C-sum PCS BKW complexities, we need to carefully select a suitable value of B. As we introduce the C-sum technique, so the number of blocks A needs to introduce the log C factor. Thus, we can get the corresponding value of B. Then, by plugging B into the above formulas, we can get the following complexities of the C-sum PCS BKW. Here we give the compression of different C-sum techniques. First, in table 1, we give the important T and M for various C-sum BKW algorithms, including original BKW, C-sum naive, C-sum desert, C-sum PCS, and quantum. And in table 2, we give the time memory trade-off comparisons of various C-sum BKW algorithms. using the most commonly used time memory trade-off notations. And in the left, we plot the corresponding curves. Look at this figure. When memory is constricted to 2 to the power of 0.3n, our C-sum PCS PKW demonstrates better performance than the C-sum dissect PKW in both time and memory trade-offs. And now I will introduce the second part, how to use graphs as a meter tool to reinterpret the PKW algorithm. First, let's look at this slide. If we want to build a graph G, we need to design a finite automaton which is naturally extended from Borger's work on LPN to fit the LWE settings. The state of LW samples, including their dimensions n and the logarithm of the number of samples m, are represented by the vertex set, and the different reduction technicals can be represented as the H set. In this way, the reduction phase of the PKW algorithm can be seen as a reduction path. Each edge can represent a reduction technique. Look at the right finite automaton, naturally extended from Borger's work. There are several specific constrictions on the order of the reduction technicals, such as the transform secret is used to control the noise standard deviation of secret. And only code reduce is related to that, so it is placed before the code reduce. And LF1 or F2 reduce, discard reduce can be used rapidly, and gas reduce is usually used to balance the complexity of the reduction phase and solving phase, so it is placed in the middle. We give the relationship between the noise standard deviation. The cumulated noise sigma prime can be completed by this formula. In this way, we can describe all of the reduction technicals in a standard formula. If a reduction path follows the order of reduction techniques in the automaton, and the nth at the state can be accepted by the Perron FFT solver, and the samples meet the requirements for successful secret recovery, we call this reduction path as a valid reduction path. Our goal is to identify the most efficient valid combination of reduction technicals. But we found that the natural extension of Borger's work on LPN to LWE doesn't elevate the high memory issue, such as the discard reduce can be used rapidly at any state, and they only consider the pairwise reduction technicals, not take advantage of the C-sum technicals. So we did some improvements. First, we integrate some memory saving reduction technicals. We explained earlier that how the C-sum technicals benefits in the low memory regimens, and we added the 3 classic C-sum reduction technicals into the original finite automaton. This is a new, this is an improved memory optimized automaton. We highlighted the reduced technicals in red. And second, we primed the potential high memory passes. We found that in the low memory regimens, some passes become impossible, so we can prime them away. We proved that no technical from reduced technicals to discard reduce can occur in the optimal reduction path and memory constrictions. Multiple code reduce is not allowed, and we removed with LF1 reduce or LF2 reduce in the state 5. And third, we rearrange the order of reduction methods, such as the discard reduce. We put it at the first between the state 1 and state 2, and we support on-the-fly sample generation. Only samples that meet the discard reduce criteria can remain in the memory. Thus, we can get the improved automaton, and we can build the new graph according to this automaton. And here are two algorithms to automate optimal reduction paths. Algorithm 2 and algorithm 3, we can identify the best automatal reduction paths. And here are our comparisons and conclusion. We first compare the time complexity. We compared our algorithms with the state-of-the-art coded BKW algorithm from the leading lattice estimator, and we highlight our improvements in bold. And then we compare memory complexities. We found that our algorithm demonstrates an advantage in memory consumption compared to the coded BKW. And finally, we compare BKW with lattice attacks. We compare coded BKW, our algorithms, and the hybrid dual attack. The hybrid dual attack demos the best performance. But our optimization does narrow the performance gap between these two types of attacks. Here are our conclusion. In this work, we give a unified framework for all BKW technicals and generalize the Bogor's framework from LPN to fit the LWE setting, and give efficient memory CV reduction, such as C-sum PCS reduce and memory optimized finite admittance. And our algorithm base coded BKW in both time and memory on all tested LWE instances. In the future, it has also some promising directions to research, such as we want to validate the independent heuristic used in the BKW algorithm, and we want to develop some general strategies to trade real time for better memory. And third, we want to research how to adapt BKW to stricter memory constrictions. Here are some important references, and thanks much.
Thank you very much, Yu. Questions for you? I have a question. Can you go back to the graph showing your results for CSUM? I think you had the screen graph. Do you remember just before the second part of the talk?
This?
Yes, exactly. So here memory is on the x-axis. That means your algorithm really improves in the low memory regime, right?
Yeah.
Where it doesn't improve on the red graph. The red graph is the old result, right?
No. The green curve is C-sum PCS.
So the green graph is yours.
Yeah.
Yes. And the red is a comparison. That's a crypto result, right?
Yeah.
Crypto 2000, I forgot.
Yes.
2017 or something.
Yeah.
So you really improved in the low memory regime, and if the memory gets too large, then the red is still the best, and there's a jump.
Yes, we only when memory is only restricted to 2 to the power of 0.3 in our C-sum PCS but we didn't beat the C-sum PCS BKW in other regimes.
Yeah, but still it's impressive. Okay, and all this assumes that you have an oracle for LWE such that you get enough samples such that BKW actually succeeds, right?
In the actually attacks, we couldn't get enough samples to attack LWE. We can make an assumption that the sample is enough to use.
I see.
Yeah.
Okay, very good. More
Thank you.
questions? If not, then please thank you again.
Thank you very much.
And we go on with the final talk of this section. Yes, I think I have them. No, this is not the first one, but that should be it. Check whether this works or not. Okay, perfect. So final talk is worst in average case hardness of decoding via smoothing bounds, and Thomas is giving the talk.
So yeah, do you hear me? Yeah, yes, I think yes. So thanks, Alex, for the introduction. So this is a joint work with Nicolas Resch. Sorry, where is the pointer? Yes, here. So this is a joint work with Nicolas Resch, and this is about worst to average case reduction for the decoding problems via smoothing bounds. So just code-based cryptography, like we had talked about lattice-based cryptography before, but in code-based cryptography, our goal is to design crypto system whose security relies on the hardness of decoding, or the problem of decoding a random codes. So when we say decoding a random codes, it means that we pick uniformly at random codes and we try to decode it. And this is basically an average case problem. So when we have an average case problem, a natural question is that, is this average case problem harder than a worst case problem? In the case of the decoding, for instance, it's also called the self-reducibility. It means that if we can decode a code uniformly at random, then are we able to decode all codes? And this is important because it will ensure us, it will give us hints about the hardness of this problem. In this talk, I will speak about worst to average case reduction, but in that case, we also call it self-reducibility. There were basically two papers doing this for the decoding problems, one from Brakersky et al. At Eurocrypt 19, and one of you et al. At Crypto 21. And both papers relied on object called smoothing bounds. So the aim of my talk is to present a bit the smoothing bounds to understand where it's coming from, etc. And so what we did with Nicolas Resch in our paper is that we developed a general smoothing bounds to offer a large degree of freedom in the worst to average case reduction, because there are many situations where we want to use this smoothing bounds for other worst to average case reduction. It's important to have as much as possible degree of freedom. And we have also shown some inherent limitation of this worst to average case reduction. And originally, we were very confident because we thought that we were able to improve the parameters of this both worst to average case reduction, but we failed, as I'm going to explain, and it's quite surprising. Okay, so my goal in this talk is mainly to present you the framework of this worst to average case reduction, and I will briefly talk about what we did, because it's quite technical and a lot of computations. Okay, so I start with the problem of decoding a random codes. What is this problem? To give you more definitions. Okay, so in this talk, I will focus on binary linear codes, which are basically subspace of the Hamming cube, f2 to the n. So I will use this notation, nk codes, where n is the length of your codes. You work with n-bit strings, and k is basically the dimensions. So as lattices, and yes, because lattices and codes are basically the same object, but we have basically two representations of codes. One which is called with a primal representation, and the other one with what we call sometimes a knapsack representation or a parity check representation, where the code is the right kernel of some matrix. And I will use the notation as with the Hamming weight, where the Hamming weight of a vector is nothing more than the number of non-zero coordinates. So now we know that what is a code. I just need few notation to speak about the decoding problem of random codes, and I will use a bit this notation after. Is that when I put an arrow like that, where x is a random variable, it means that x is an element which is picked uniformly at random in the set S. And this notation here, Bernoulli P O times n, means that my vector E, each of its coordinates are picked according to a Bernoulli of the same parameter and independently. And if you're not familiar with this, think that this is a Gaussian. It's the same thing for lattices. It's exactly the same distribution, but in another context. And the Bernoulli distribution n times independently gives you typically words of Hamming weight np. So the decoding problem of a random code is stated as follows. I give you a matrix A, which basically represents the basis of a code, and this basis is chosen uniformly at random among all the possible bases. And I give you an element of the code, SA, plus an error E, which is picked according to the Bernoulli distribution. And your goal is to recover S or equivalently E, etc. So here I use this notation, which is a decoding problem of a random call in its primal representation, but we have an equivalent formulation, and sometimes people call it syndrome decoding problem, but it's exactly the same problem, just here that we write the problem in its dual form. And also another thing, maybe you heard about the LPN problem, but in LPN there is a subtlety that you have access to an unlimited number of samples, where here I limit the number of samples n. Because basically here I have n samples of my vector. So strictly speaking, LPN is an easier problem than decoding random codes because you have this freedom on the number of samples. Okay, so now we have this problem. Let's go to the worst to average case reduction, the self-reducibility. So our goal, what is our goal? Our goal is to show that if I can decode in average, then I can decode all codes. So I start with an instance, a fixed instance of the decoding problem. So I think once for all, our God gives me some instance of the decoding problem, a basis, and a noisy code word. And our goal is to remove the error or to recover X. But what we have in our pocket is only an algorithm A solving this problem. Not this problem, this one, but solving the average decoding problem with some probability epsilon. So basically it means that my algorithm A succeeds to decode on a fraction epsilon of the instance. And I want to use this algorithm to decode my fixed instance. So how can we do it? And yes, and basically what I'm going to present, it works exactly in the same way for LWE, and this framework also was, in the code case, was introduced by Brakersky et al. So it's not our result in this part. And for LW, it's exactly the same way that we do. Okay, so the idea is that we start from this fixed instance, and we want to build some kind of uniform instance of the decoding problem. So the natural thing to do, not natural at first sight, but is to pick an error here according to some distribution. But this distribution thinks that we can choose what we want, whatever we want. We are free on this distribution. And then we compute the, I call this vector y, and I compute the inner product between e and y. So I use the linearity, I do my sum, and what I observe here is that when I decompose like this, I obtain here, in fact, where x is what I want to recover at the end, I obtain, in fact, one sample, like one LW sample or one LPN sample, if you want, here, where this is a secret, and this plays the role of my colon, which is supposed to be uniform in LWE or LPN. And here it is a noise. So for the reduction to work, we need E times G transpose to be close to uniform. It's what we need to ensure. And this is a noise, it's a bit of the noise, so we can analyze this. It depends on the choice of the distribution D. Okay. So all our goal is to understand how can we can transform this into an object which is close to uniform. Okay. So a natural thing that you can say is that, okay, I want this to be very close to uniform, so what can I do? Is that I can choose E like a uniform vector. But if you do this, in fact, what will happen is that the noise that you will build here will be also uniform. So it means that you cannot solve your average problem. So in fact, what we see here is that we have two contradictory requirements. We want this bit to be small as possible, but at the same time, for this bit to be as small as possible, we want E to be small. But how can this be uniform if E is small? It's exactly why you have all the contradictory requirements in all worst to average case reductions in codes and lattice-based cryptography, basically. It's coming from these two opposite things that you ask. Okay, so what the conclusion of this is that we need to carefully choose this noise, E. Okay. So to understand how we choose this noise, before that, remember I said that I want this to be close to uniform, and what do I mean by close to uniform? I will use the notion of statistical distance. If you're not familiar with statistical distance, basically it is a distance between two random variables, which is the L1 distance between them, and the moral of statistical distance is to say that, oh, if I have an algorithm which succeeds with probability, let's say epsilon, when I feed to him inputs according to a random variable x, if I change the random variable x by another random variable y, then my algorithm succeeds with the probability basically epsilon minus the statistical distance between x and y. So if the statistical distance is small, then you are done. You don't change anything when you change the random variables in your algorithm. So the closeness that we are going to use now is that we want E times G transpose to be close for the statistical distance to the uniform. Okay, but if we are more formal, what we want to upper bound is this statistical distance. Here it is the decoding samples that I can build from my fixed decoding instance, and here are the real, true decoding, random decoding instance. And I want to upper bound this statistical distance. And then if I succeed to do that, then I will feed to my decoding solver A this instance, and as I know that my algorithm works with probability epsilon over this input, then if I feed to him n instance, it will succeed with at most this probability. So all the game now is to estimate this statistical distance. And for the rest of the talk, I will simplify a bit this statistical distance by only speaking of that. Or this is basically the same one, same statistical distance. Instead, that with this statistical distance, we have a rather more complicated formula which involves some coset of the code. Okay, so now our goal is to upper bound this statistical distance. So how can we do it? So me, when I see this, to be honest, the first time I saw this, I'm not very, I don't see what it is. This E times G transpose, this is not very nice object to deal with. But in fact, this E times G is nothing else than a coset representative. Or if you think about lattices, you work in the fundamental parallelepiped. It's exactly what you do. So if we take the code or the lattice point of view, what we do is that we consider the code C, which is the left kernel, or the right kernel, not of the transpose, but the left kernel of the transpose of this matrix, G. This basically means that the dual of this code is generated by the row of my matrix. So my matrix G here gives me a basis of the dual of this code. And in fact, E times G transpose defines the coset of the code. By this, I mean that if I want this to be uniform, this is nothing else to be uniform modulo the code, or the fundamental parallelepiped. So asking this to be uniform when I pick E according to a distribution D, it exactly means that I want C plus E to be uniform in the Hamming cube when I pick C uniformly at random in the code, and I add the error according to my free distribution D. Okay. And all smoothing parameters, in fact, deal with this, ensuring that this is uniform. And this is a nice point of view in its primal form, let's say, where here it's a point of view with dual form. And to my opinion, this form is more geometric and intuitive. Okay. So if we draw a picture with potatoes, what do we want? We want, starting from a code word C here, the red bullet, uniformly at random. And after, if I add a noise, I want this to be uniform. So what we see directly is that if my noise concentrates on the balls, then I need my balls to be of size large enough. And remember, in the worst average case reduction, I said that I want to add as less as possible noise for the noise of the average case problem to be as small as possible. So all the question is that what is the minimal amount of noise that I can add here for this to be uniform? And the answer is called in coding theory as the Gilbert-Varchamov radius. In lattices, it's called the Gaussian heuristic. And it is a combinatorial bound that tells you that, okay, it is the smallest radius such that the volume of the ball, of my ball here, times the number of code words is bigger than the size of the whole space. So this is, we call it in coding theory, Gilbert-Varchamov radius, while it is a Gaussian heuristic. So what do we want here, if you want to have an optimal worst average case reduction? We want to be sure that we smooth at this radius. It's the objective. So it's what we try to do. And for that, I'm going to present now a bit quickly what we did with Nicolas, and yes, about what we call the smoothing parameter. And the smoothing parameter is basically the minimal amount of noise that we can add to ensure that this is uniform. So what we did is Nicolas, we obtained this bound. Okay, so a bit of notation, sorry, before. Yes, here unif denotes the uniform distribution on my space. I target this. This denotes the indicator of my code normalized. This is nothing else than the uniform distribution over the code. This is a convolution product with F, which denotes my distribution that I can choose as I want in my worst average case reduction. And why the convolution? Because these two distributions are independent, and this is nothing else than considering the distribution where I pick uniformly at random code words, and I add an error according to a distribution F. And I want this to be small. And so we obtain this very beautiful bound. So I won't explain how, but in fact the proof is very natural. It uses Cauchy-Schwarz inequality and Parseval identity. And as you see, it involves the weight enumerators or the weight distribution of the dual of the code. Okay. And what is this code? Remember, C is the code that were obtained as the left kernel of the transpose of my matrix G, which was fixed at the beginning. So now the question, I want to choose F such that this is negligible. It's all the game. But the problem of this bound is that when we see it, I don't really like this quantity because I don't know how to deal with at first sight. So what we did how we proceed is that we said, okay, in our dream, what we want this to be negligible. We have F which concentrates, let's say, over words of Hamming YT, and our dream was to say, we want this bond to be negligible as soon as the radius where the F concentrates is bigger than the Gilbert-Varchamov radius. Okay, and it's our dream, and if we succeed to do that, we obtain an optimal smoothing noise. So what we did first, we said, okay, I don't understand how this bond behaves very easily, so what I can do, I can look at the expected value of this. So I will average over all the codes to understand how it behaves. If this average is small, then it's small for almost everyone. And what is nice is that when we do the average, we obtain a beautiful bond like this, where now it only depends of F, which is our free distribution. Okay? So now we can choose F and look at how behaves this bond. And what was surprising when we did all of this is that at the origin we said, oh, okay, for smoothing, we consider the Bernoulli or the Gaussian, everyone is doing that. And in fact, what happens is that when you consider f as a Bernoulli distribution to smooth, then with the previous band that I gave, we obtain that we smooth only for a radius largely greater than GV, which is the optimal bound. So it's like that. Our band is not cool for this Bernoulli distribution. After we said, okay, it's very strange because we thought that our band was very tight, etc. And we choose another distribution for smoothing, which is, this time, we take a uniform distribution over a sphere of radius t. And with this choice of distribution, we obtain that our smoothing band is optimal. By this, I mean we can ensure that we smooth as soon as our radius is equal to the Gilbert-Varchamov radius. So a conclusion, first conclusion is that our band is really tight. It enables to smooth at the optimal parameters. And then this is a very good choice of distribution for smoothing. Okay. But remember what I did now. If we want a worst average case reduction, C is fixed by the worst case instance. And for now, I only consider my band in average over all the C. So what I did, strictly speaking, is an average to average case reduction. So what I need to do is to upper bound and the weight distribution of the dual of the code. And at the time with Nick, we said, oh, this we know many things we know how to upper bound this. We know very powerful bond to do that. And when we looked at the paper, the first paper doing worst average case reduction, they were basically using that this implicitly they were using that this for all u is smaller than the size of the code. So we said, oh, it's a trivial bound, so we can do better, etc. So what we use the best known upper bound on this weight distribution, which is basically called the second linear programming bound. And we said that thanks to that, we'll improve the parameters of the worst average case reduction. And we failed. And it turns out that for parameters of interest for the worst average case reduction, strangely, the second linear programming bound, which is the best known bound since 50 years on these quantities, is very weak. And we completely failed at this point, and we are very surprised. So it really shows that for the parameters of the worst to average case reduction, we need new result about this kind of object to improve the parameters of the reductions. So as a conclusion, and I will stop here after, what we did is that the worst average case reduction for at least codes now can be instantiated with any distribution for the smoothing part. We wanted to have this large degree of freedom. Apparently, the Bernoulli distribution, it's the same for lattices. The Gaussian is not a good choice with our bound to obtain a smoothing parameter, but hopefully, in fact, a Bernoulli distribution or a Gaussian is extremely concentrated on the sphere where it concentrates all the mass. It's basically Chernoff bounds. And in fact, we can also smooth optimally with Bernoulli or Gaussian by truncating arguments. So I cheated a little bit when I said the Bernoulli is not a good choice. It's not a good choice at first sight, but we can use it. And in the paper, I didn't explain this a lot. We have also shown that there are some inherent limitations to the framework of the worst average case reduction for the parameters. Okay, so thank you very much.
Yeah, thank you very much, Thomas. Questions to Thomas? So since you draw this conclusion, this comparison to lattices all the time during the talk, if you compare the results now to lattices in terms of tightness of the reduction.
No, I didn't compare. It's not very clear each time for the self-reducibility of LWE, but what is sure is that, the smoothing parameters that we use can improve a bit the parameters of the reduction. But in the lattice case, they are lucky because they have a large magnitude of freedom in their parameters and
there's a
change
queue.
a bit. So,
Okay.
and in the code case, we have to be very tight. So it was the initial motivation of it.
Is there anything known for other metrics other than Hamming?
For this kind of
worst case to average case, like rank or for rank metric or something like that?
Yeah, we could do it also for the rank case, and also for the Lie metric. But all the problem is that if you want to do a worst average case reduction, you need to have a upper bound on this quantity.
Okay.
And so, for instance, in the Lie metric, we don't have results on that. But as we use a trivial upper bound, maybe we can use it also. But yeah.
Okay. Well, that's nice to know.
It
More
will work.
questions? Oh, I see everybody is hungry. That's also good. So let's thank all the speakers of the session again. Okay, and we have food in the usual place, I guess. And we reconvene at 1:20 for the next session.